Hi guys, I'm GKCS. We are talking about snake eats from the Codechef Snackdown challenge this time. And this was the toughest question in the pre-definition round. So what we have is lots of snakes. So it's snake-based theme this time on Snackdown. And we have lots of snakes of different lengths, which is Li. So lots and lots of snakes. Okay. And each one has the length given by Li. So one of these snakes, the largest snakes, can eat one of the smaller snakes, like cobras do, like king cobras. And what will happen then is that the length will increase by 1 for the largest snake, and for the shortest snake it will die. So that length becomes 0. So you lose that snake basically in your zoo, whatever you have. Now the thing is, what you need to do is you need to answer Q queries such that you'll be given a number k. Okay, and this is the length that you are looking for. So you'll be looking at all the snakes, and you'll be looking at how many snakes at most can reach length k. So you have to print that number out for each query. Simple enough, just find out how many snakes can reach length k and print that number. So Q queries, Q is quite a bit. The number of snakes is equal to n. So n is 10 raised to the power 5, Q is 10 raised to the power 5, and ONQ solution will not work. So simple solutions are taken out. Let's just jump to the right solution, because this is one of those questions where the right solution is actually as obvious as the other brute force solutions. Okay, so firstly, we are looking for a snake of length k. If a snake is already of length k, is it useful to have that snake at all in any kind of action? Okay, if a snake eats another snake, its length grows by 1. So if you have a snake of length k and it eats another snake, its length increases, but the overall count of snakes which are of length k does not increase. So there is no point in having a snake eat another snake if it all is already of length k. So that's taken out. The second thing is, if a snake is of length k and another snake eats it, you're actually losing a snake of length k. So the overall count is going bad, right? You want the maximum number of snakes which can hit this length. You just lost a snake. So never will a snake of length k or greater participate in the eating process for a query where you have k equal to this. Okay, so that part is taken care of. That means that amongst all the snakes, we'll be removing all the snakes having length greater than or equal to k. Okay, these will be removed, and the only ones therefore that you're actually working with have length less than k. Okay, this part is very simple. Now let's look at a strategy to use to solve the problem. So the strategy for this is very simple. What you have is, you have all the lengths given to you. You can iterate over the snakes and find out those having length greater than or equal to k and remove them from your list. So that will be an order n operation, because you're checking every snake. Okay, and now you have this modified list where all snakes from 0 to, let's say, a number x have lengths less than k. Okay, this is your modified list. What do? Well, your strategy should be, pick up the snake having the maximum potential to reach k and feed it that snake which has the minimum potential to reach k. Okay, that's a pretty obvious strategy, but it works here because you pick up the snake, let's say over here, which has a number k minus 2, and over here you have k minus 10 and k minus 9, so on and so forth. And you feed this snake to this one. So this becomes of length k minus 1, then you feed this snake to this one, and then it reaches k, the largest snake. And now you can remove it from your list. So what you're doing is you're removing snakes from your list based on a strategy. Okay, and this is correct also. However, there's a problem. If you do this in a very manual manner, okay, the largest snake, to find the largest snake in your remaining list will be an order n operation. To find the smallest snake will also be an order n operation. And, well, eating is an order 1 operation, so that doesn't count. Overall, for every query, you will require order n operations, which is order qn, finding the max and the min. Fine. How can we improve on this? Simply put, we can sort. We can sort all the remaining snakes. And how do you sort it? Well, we use a library function in any language. So sorting is a pretty common thing. So in fact, the array I had was already sorted, but yeah, 1, 1, 6, 8, 8, and 10. This is sorted in terms of lengths. And what we'll do here is if k is equal to 12, we'll feed the snake of length 10, the snake of length 1, and then again this snake. And once it hits 12, we remove it from the array. So at any given point of time, you know what is the largest because it's at the end of the list. And at any given point of time, you know the smallest because it's at the beginning of the list that you have. Okay, even here though, you have a problem. Every query will at most take order n time. And why is that? Well, you come here, you picked up the smallest snake 2 times. Once you came here, you try to pick up the smallest snake 4 times. And so you're seeing that for every snake which you're trying to hit up to length k, you're also traversing from the left of the list up to that point in the worst case. So in the worst case, this is an order n operation. And for every query, that will turn out to be an order qn operation. Overall solution, still not good enough. Okay, so what can we do? The first thing we are going to do is make an observation. This snake needs, well, k was equal to 2, right? I don't know why I rubbed that off, but yeah. This snake needs 2 more snakes to hit k. This snake needs 4 snakes to hit k. This one needs 4 too. So what we are seeing is that just by looking at a number, we can tell how many snakes we need to skip from the left. So can we just pick this up and solve our problem immediately? No, because you could have the array of all 11s. Okay, this is a weird way to have the array. You could have all 11s in your array, and then this snake needs 1 snake to reach k. So that's one computation. This snake again needs 1 more snake to reach k. That's another computation, and so on and so forth. So half the number of computations of the length of the array. So that is order n by 2, which is order n for each query. So we're still stuck there. But this is a very good observation because if you know how many snakes you need to actually reach k, we can make other observations now. What could they be? Well, if we had the sum of requirements of these snakes, we could find out if we can meet that requirement using the other snakes. Okay, take your time to understand this. If you knew the sum of requirements, meaning if you knew that this requires 2 and this requires 4 and this requires 4, if you know the sum of requirements for a range of snakes from the most potential to the least potential, then you could tell if you could actually hit that number using the remaining snakes by feeding these snakes to the other big guys. All right. So, what is your requirement? Well, for a range of x numbers, so you're trying to reach k for x snakes, you need k into x. That's what you need, right? Points, like length, minus what you already have. So minus 10, minus 8, minus so on and so forth. So minus the sum from 0 to x is what we said. So comma x. This will be the range ending, and the range start will be x minus, let's say the length of the range is small l. So x minus l plus 1. Okay, that is a technicality. This is how much you need. This is how much you already have. So the difference is your requirement. And your requirement should be less than or equal to the supply. Supply is equal to x minus l plus 1. Why is that? Well, because these many snakes are remaining. After you have, taken this range, these many snakes are remaining to be fed to the big guys. So this is the equation that you have. Okay. And yeah, that's it. Actually, this is it. What is your job here? Well, L is the length of the range that you can have from this point. So your job is to maximize that range. Your job is to maximize small l. So in the best case, you will be having this equal to x minus l plus 1. So whatever supply you had, you completely consumed it. And otherwise, well, this is the condition. Less than is also fine. It's fine. So how do you find the maximum value of L here? We could use something called binary search. Okay. If in case something is coming in your mind that how do you find the value of x here, we'll come to that later, because the binary search there is going to be slightly tricky. So first let's think about, we have already got that magically somehow, all numbers less than k. To maximize L, what you could do is start making assumptions for L. Okay, let's say L is equal to n by 2. Okay, or the smarter thing to do would be, actually, this is the length x, right? So L is equal to x by 2. That's how we start. If this equation holds, then we get greedy and we go for more, right? The maximum that L can reach, by the way, is x. You know, all elements could be in the range. That's the maximum that L can reach, small l. And the minimum that it can reach is 0. None of the snakes can reach k. So the range is 0. So this is the range that we are playing with. It's very similar to binary search, in which we play from the start to the end. The length of the array has the range. Okay, so 0 to x is the range that you have. Now, of course, you start with left range plus right range, so 0 plus x by 2, which is x by 2. This is your first assumption. If this case holds, if this equation that we talked about holds, then we change x to the right hand side. So that becomes, what does L become? L becomes then x by 2 was its original value, so that becomes your new smaller bound, plus x, the whole thing by 2. So this becomes 3x by 2. No, it becomes, well, x is taken common. 1.5 is what you have, and that is divided by 2. So that is 0.75. 3x by 4 is your new range, if this equation holds, right? If the equation holds. If the equation doesn't hold, then this becomes your right bound, which becomes x by 2, and your left bound is still 0. So this turns out to be x by 4. Okay, so effectively what you're doing is you have this big fat array, and you started off in the middle, just like in binary search. In case the equation holds, you go to the right, you get greedy, and go to the middle of whatever remaining range you have. In case it doesn't hold, then you go to the lower range, and you go to the middle of that, so that is x by 4. And this is 3x by 4. And this is x by 2. Okay, simple, just like binary search. So in this way, what will happen is you will find the best value for small l. Because at one particular point, you'll see that anything more than this value for small l will be too much, and anything less than will be too little. So that will be the perfect place for small l. Okay, you'll find that somewhere in this array. Perfect value for small l. And that will be it. That's all you need to actually output. Small l is the answer that you want, the maximum number of snakes which can hit length k. Except for one small thing. I said that we can filter out all the values greater than or equal to k. But how much does filtering out take? I mean, how much time does it take? Order n. That's bad, because every query, if it takes order n time, that's too much, because order qn time will be the overall complexity. So what we can do here is using simple sorting, we can sort all the lengths. Okay, and everything greater than k will appear here, because this is the point where all numbers smaller than k exist. Everything greater than k will appear here. And we can just binary search for k in this array to find the point at which k should exist, right? So let's binary search for k. Let's say there's a value 12 here, 13, etc., etc. You binary search for 12. You come to this point. You see 12 exists. That's awesome. You pick up all these numbers and add them to your count. So count is initialized with all these numbers. And then later on what you do is you just add L, the perfect value that you can get, to the count that you have. And finally you just print count. Okay, this is plus equal to, but I think I'll make things simpler, L plus count. Right, you initialize that, add whatever value that you can, the maximum range that you can, and then you print that. So this is your answer. There's one small thing remaining here. We said that we can remove all elements greater than or equal to k in order and time. But that's the place where we already lose our solution, where we lose all the hope. Because if it's taking order and time per query, then it's going to take you order queue and time to solve the problem, which is too slow. Okay. So what you should do is you should sort the array initially itself. If k is equal to 12 here, we sort the entire array, and we do this just once. So that is an n log n operation. When you have the first, when you get to see all the snakes, that's when you sort the whole array. And for different queries having different k's, we will be evicting out all elements greater than equal to k. So in this case, let's take this example. We have sorted the array. We get a query of k equal to 12. So these elements should be taken out. How do we do that? Binary search. So what should we binary search on? We should binary search on something slightly less than 12. Right? There's a general way to take care of this, but the thing is it's going to get a little complicated because there are duplicate elements here. So what I will be doing is binary searching for the value 11.5, and all the lengths of the snakes are integers. So if I binary search for the value of 11.5, there's no way that this array will have 11.5 in it. Okay, that's one of the properties of binary search. No, in fact that isn't. What I'm going to say right now is a property of binary search. 11.5 won't be found in this array, but the point where your binary search will stop is called the insertion point. Okay, that's one of the properties of binary search. If binary search fails, it tells you exactly where that element should have existed. Should doesn't, but should. So, like in Java, you get the insertion point every time you run the binary search. If it fails, then you get it as a negative value. Okay, but let's see how that actually works. So 0, 1, 2, 3, 4, 5, and 6 are the indexes we are playing with. We are going to binary search on this. So lower and upper is 0 and 6. By 2, this is the new mid. What we have is 3. So we should go at index 3 and check. Is 11 less than 12? Yes. So we should go on the right. All these elements are discarded. Okay, 13, and 16. But we don't know that because our lower bound is 4 and upper bound is 6. And the middle of that is 5. So we come here. We see, is 13 greater than 12? Oh, I think I made a small mistake. Well, we said that we are going to be searching for this. So, no changes yet. We came here, we saw that 11 is less than 11.5, and we ignored this entire array, okay? So 11.5 is what we are searching for, and we ignored the left part. We have gone on to the right. Yay! Now, this is 13. 13 is greater than 11.5. So, we should have ignore the entire right array along with this element. So, this array is ignored, this subarray. What you have remaining is this part, 13. So, you come here, your new mid is 4 plus 4. Let's write that down, 4 plus 4 by 2 is 4. So, this is your mid, you search here. you see that 13 is not equal to 11.5 and you have run out of array now. So this is your insertion point. This is where 11.5 should have been had it existed in this array. So your insertion point essentially is 4. Okay. Because your insertion point is 4, what that says is that every element from 4 onwards should be ignored. Why? Because every element from 4 onwards is greater than or equal to 11.5. Is not actually greater than or equal to, it's greater than, strictly greater than 11.5. So every element where I goes from 4 to whatever value n has is greater than, what was it, 11.5. What this tells you is that every element less than this should be taken into consideration and all these elements need to be discarded. So that's the way you find x. X in your case is 3. You need to take care of elements from 0 to x. Okay, so initially count will become 3, and for whatever value of small l you get, you'll add that to the count, plus equal to l. So that's how you'll be solving this problem. So that's it for this problem. It's a pretty neat way to solve it. Like, this is a good trick to have up your sleeve because in a contest you don't really want to be thinking about the general solution. However, of course, this is not the general way to solve a problem in which you're trying to, filter out numbers greater than a particular value using binary search. So in case you have that with you, you can post that in the comments. And if you have any doubts or queries, you can please post them there too. I'll be happy to help. I'll be posting a few more videos on binary search because this is a topic that we should know very, very well. So I'll be having 2 more questions on binary search. One from Code in Game. It's a brilliant site, you should check it out. And one from, what was it, Code Forces, yeah. They had a div 415, yeah, as binary search. So you can subscribe if you want notifications for that. And this is a subtle way to say that please subscribe. So until next time, see you.